All right, let's get started. Okay, welcome back, and so let's get started with a quick recap of what we have done last week before the break. Okay, so we introduced the concept of state machines that kind of culminates everything that we have been discussing so far in this course. Okay, so we'll be applying all the things that we have learned and putting together those things, those building blocks to fabricate or to construct these state machines. Okay, so what are state machines? Again, just to give a quick recap because you had a long break. State machines. So these are machines as the name suggests, right? So these are machines that can exist in multiple states. So far, we haven't done that. So far, we have been dealing with combinational building blocks, and combinational building blocks are not really machines that can exist in multiple states. It's basically, that's a machine or a circuit that can only exist in one state. Okay. We have also dealt with the essential building blocks of sequential circuits, but really not putting together everything to construct machines that can exist in multiple states. Okay, and in the last class, that's exactly what we have done. So we examined how we can construct machines that can exist in multiple states that can actually sequentially perform operations without external inputs. External inputs, as in the user providing the inputs each time. Okay, so once they are programmed, once they're constructed, and once they are set into operation, then they can be made to run autonomously, if you will. Okay, all right. So what are the characteristics of a state machine? So in the last class, we looked at these are also called finite state machines because we are dealing with state machines that consist of finite number of states. Okay, and okay, so I may have to. Okay, let me see here. Yeah, there you go. So this is what we're going to talk about today: state machines. Now, the characteristics of state machines. How do we construct one? Right. These are machines that can exist in multiple states, and some of the characteristic terms associated with these machines are state diagrams. Okay. Again, this is a diagram that depicts, that's more like a snapshot of a state machine. Like it basically provides all the information about the state machine in terms of how many number of states that does the state machine have, and how does the state machine transition between one state to the next state. Okay, so that's basically a snapshot. Once you look at that snapshot, you'll exactly understand that about that state machine in terms of, okay, if this machine is in this particular state at a given instant of time, this particular input acting on that state machine or on that state would transition that machine from this state to the next state. So that the diagram provides all that information in a snapshot. Okay, so it's very informative that way. So what does this diagram consist of? Basically, you will have um, this particular diagram. You will have the state information, states that are represented by these circles, right? Each state, again, because we are constructing state machines as digital systems. Again, you need to ensure that each state is encoded with a unique binary code. Okay, so each state is encoded with a unique binary code, and it's the state variables that encode these codes, right? So all the state information is encoded in the state variables. Okay, now so let's say I have multiple states, and then this particular diagram basically gives me a snapshot of how the state transitions occur given a particular input acting on a particular state, and let's say x equal to 0, let's say takes me back to the same state, x equals 1 takes me to the next state, and so on. Okay, so those inputs and the present state at any given time determine what my next state should be. Okay, that's the idea here. Okay, so that's the state diagram. State diagram. This is very important aspect in the construction of a state machine. Then the next thing that you need to be aware of or to remember is the block diagram, the general block diagram of a state machine, which we discussed in the last class. So we discussed the state diagram in much detail in the last class. So now the other important thing that you need to remember to get adept at designing state machines is the block diagram. It's again, the block diagram itself is not complicated, right? But what you have is a combinational block, okay? As you can see here, it is kind of evident here, right? So each of my state itself is encoded as a unique code. For example, let's say S0 is encoded as, let's say I have 4 states. That means I need to have at least 2 state variables, because I need I need to have at least 2 bits to encode each each state, right? So I need to have at least 2 state variables, and typically they are represented as, in terms of AB, and so on. So in this case, S0 is encoded as 0, 0. S1 is encoded, let's say, as 0, 1. S2 is encoded as 1, 0. S3 is encoded as 1, 1. Okay. So again, my state encoding is basically saved in my state variables. My state variables encodes the state information. Okay. All right. And what else? So that's my block diagram. As you can see here, again, my next state and depends on my present state. So I have in the block diagram, I have the combinational block, basically that combines the inputs, right? The inputs along with the present state. These are my inputs. I can have multiple inputs along with the present state. Let's say I have in this case, 2 states, two state variables that encode those 4 states. Okay, and the next state. So next state is the output of this combinational block. And the next state is the output of the combinational block. How do I compute this? I compute this based on the present state values at a given instant of time and the inputs, right? Present state and the inputs determine what my next state should be. So this combinational block does that for you. So you need to ultimately design that combinational block, and of course you may have some outputs as well. Okay, and the number of state variables I have, that determines how many flip-flops I'll be using. Okay, because each flip-flop basically stores that once the flip-flop basically stores the state information during the clock cycle. Okay. So these outputs go into the inputs of the flip-flops, and then you have this feedback, so that in the future, my futures, because these are your future states, right? In the future, my future state becomes the present state. That's why you have this feedback. That mechanism is signified by this feedback. So that's my Q A, Q B. This is my DA, DB. Okay. So my future state becomes my present state by this feedback. So that's the basic block diagram that you should remember. Okay. Okay. So ultimately, all it boils down in the design of a state machine is you have to basically design this combinational block. And this is what we have done in the last class, looking at an example where we looked at the example of a JK flip-flop. So basically we wanted to design a JK flip-flop from a D flip-flop, right? And the way we did that is we first came up with the state diagram for a JK flip-flop. Again, the important aspect in the design of a state machine is how do you define the states. Okay, again, when I'm going back to the strategy of solving these kind of problems or the design of state machines, the approach that we take is you're given a problem statement, you identify what the inputs and the outputs are, like you always do, right? And in the design of a state machine, you also have to identify the states. What constitutes a state? That's something that you need to decide, and based on that, come up with the different states. How many states you have, okay? And with that information, you translate all that information into the state diagram. Okay, so basically providing a snapshot of how the state machine should work. Okay, given all possible combinations of the inputs and the states. All right, and once you have that information down, then the rest of the steps are pretty straightforward. You put that information, you translate the state diagram information into what is called a state table. Okay, And again, the state table has a specific format that you need to follow, right? We have and we have seen that in the last class. And from that, you will be designing this combinational block. You will be determining how many flip flops you will have. That's determined based on how many states you have in your system, and then ultimately the problem boils down to the design of a combinational block, which we already know how to design the combinational block using the K-map approach and so on. So from then on, it basically becomes very straightforward. The main important parts are coming up with the states. How do you assign states? What do you mean by the states in that for that particular system that you're trying to design, and coming up with the state diagram. So that's the main important parts. The rest of them are pretty straightforward. Once you understand the technique, it should be pretty straightforward. Okay, so this is what we have done in the last class. All right. Now in this class, let's pick up from that aspect, and let's look at a few more designs, examples. Okay. So in terms of state machines, I can classify these state machines into two types. Okay. Again, these are called finite state machines. So I will express these as FSMs, finite state machines. All right. Now I can classify these into two types. One is called what is called the Moore type state machine, and the Mealy type. Again, the only difference between these two types of state machines is the way we specify the outputs in the state diagrams. Okay, and of course how we implement these outputs. That's the only difference. Okay, but of course that's an important difference, and you will see why. Okay, so now let's actually describe what is the Moore type state machine. Let's start with the Moore type. So here is a state machine whose state diagram is specified like this. So in this particular case, my output is a function of the input at any given when I'm working with this kind of state machine. At any given instant of time, the output of that state machine is a function of the input as well as the present state. Okay, so it's a function of both the input as well as the present state. So when I'm trying to specify or when I'm trying to draw a state diagram for a Moore type machine, it will look something like this. So let's say I'm looking at a simple state diagram for a state machine which has, let's say, 4 states. Okay. Again, my states are represented by the circles. So let's say I have 4 states: S0, S1, S2, and S3. Okay. So in this case, my input specify again. This is some kind of some arbitrary state diagram. Okay. So here, let's say my x is the input for this particular state machine, and let's say y is the output. So my inputs and outputs are specified at the same time. Okay. So let's say x equal to 0 takes me back to a 0 state. Okay, let's say that's how we define this particular state machine. When I'm in a 0 state, x equal to 0, that's my input. Take me back to the same state, back to the 0 state, and producing an output of y equal to 0, let's say. So as you can see here, the way I specified the output, I'm specifying the output along with the input, with this slash, of course, to differentiate between the input and the output. Okay. So my output depends on both the input as well as the present state. So that's how we specify the inputs, the outputs for a Moore type state machine. I'm sorry, this is the Mealy. This is a Mealy type. I kind of got it mixed up here. Let me say. This is a Mealy type machine. Okay, Mealy type. So I'm describing the Mealy and the Moore type state machines. Please note the correction here. Okay, that's the Mealy type state machine. Okay, so the outputs are specified along with the inputs. Again, I can complete this diagram. So again, let's say x equal to 1 takes me to S1 state, providing me an output of y equal to 0. All right. And now I'm done with the S0 state. Again, this is a basic recap of what we've already done before. The process of coming up with the state diagram is not different than what we have seen before. Okay, when we worked on some of the examples in the last class. So again, I would work with each state at a given time and work with and look at all possible combinations of the inputs. So in this case, of course, I have a single input. So the only thing I have are x equal to 0 possibility or x equal to 1 possibility, which I have covered in this case. So now I move on to the next state and do exactly the same process. So if I'm in S1 state, let's say x equal to 0 takes me back to S0 state. X equal to 0 takes me back to S0 state. Let's say producing an output y equal to 1. Again, this is some arbitrary state machine. Let's say x equal to 1 takes me to S2 state, providing me an output y equal to 0. Okay, and so now I'm done with S1 state. Now I move on to S2 state, do the same thing. Let's say x equal to 0 takes me to S3 state, providing me an output y equal to 1, and x equal to 1 takes me to S0 state, providing me an output y equal to 0. Okay, and finally, so I'm done with S2 state. I'll move on to S3 state, do the same process. Let's say x equal to 0 takes me to S0 state, providing me an output y equal to 1. X equal to 1 takes me back to S3 state, providing me an output y equal to 0. Some arbitrary combination of inputs and outputs. Again, I just want to describe how this Mealy type diagram actually looks. So a state diagram that looks like this, where the outputs are specified with the inputs, where the outputs are functions of the present state as well as the input, the present input, is a Mealy type machine. It's classified as a Mealy type machine. Okay. All right. So that's how a Mealy type machine would look like. Now let's look at the Moore type. All right. So this is a Moore type. Now, in the Moore type of a state machine, the outputs, this is very important, the outputs are functions of the present state itself only. Outputs are functions of the present state only. Okay, and that has a very important consequence of having the outputs functions of the present state only. In this case, the outputs, let me actually write it down. For the Mealy type, the outputs are functions of present state as well as the inputs. And that is signified by the way we draw the state diagram in this case. All right. For the Moore type, again, let's come up with an arbitrary state diagram that would be corresponding to a Moore type state machine. So let's say I have S0. I have, let's say, 4 states, S1, S0, S1, S2, S3. Now in this case, because my outputs are only functions of the present state, I would specify the output along with the state. Okay, so in this case, this is how I would specify. And of course, as a matter of fact, in the last class before the break, the way we designed the JK flip-flop, we designed it as a Moore type state machine. If you recall, the outputs were specified along with the state. So let's say my output here is y. Okay, so if I'm in this particular state, irrespective of the input, my output is specified. Because my outputs are functions of the state itself, my output is 0. Let's say, assuming that in this particular state, my output is 0. So y equal to 0. So let's say this particular state is associated with an output of y equal to 1. Let's say this state is associated with an output of y equal to 0. Let's say this S3 state is associated with an output of y equal to 1. All right. And now, of course, the inputs and the present state, as always, determines the state transitions. Okay, so let's say x equal to 0 takes me back to the same state. When I'm in a 0 state, x equal to 0 takes me back to the 0 state. Okay, and as long as I'm in a S0 state, my output will be 0. As long as I'm there, the output will be 0. Let's say x equal to 1 takes me to S1 state, and as soon as I enter the S1 state, my output becomes 1, because my output is a function of the state itself. Again, so I'm done with S0 state, I move on to S1 state. Let's say x equal to 0 takes me to S2 state. When I'm in S1 state, x equal to 0 takes me to S1 state, and then let's say x equal to 1 takes me back to the same state. All right, and I'm done with S1 state. I will do the same thing. X equal to 0, let's say x equal to 1 takes me to that state. I'm done with S2 state. I will do S3 state. Let's say x equal to 0 takes me back to S3 state. X equal to 1 takes me to S0 state. So I'm done with my state diagram. So a state diagram that looks like this, where my outputs are specified along with the state, would constitute a Moore type state machine, because my outputs are functions of the state itself. Okay. So now what's the big deal between the difference? What's the big deal between the difference between these two states? Right. All right. So let's see. I've been talking for a long time. Let me see if you have any questions about anything so far before we move on. Are you with me until this time? Just speak up, because I can't see your text message. Okay, so you're still with me, right? Okay, very good.
Yes.
Okay, good. So the difference is the consequence of this, where for the difference between the Mealy and Moore type. Okay. Now, in this case, as you can see, as is very obvious here, my outputs are because my states itself are contained in the flip flops, right? The state information. My outputs, because these are functions of the state itself, these are automatically synchronized with the clock. So even if my input changes during a clock cycle, my outputs are fixed. My outputs don't change unless unless I have a state transition occurring. Right? Unless I move from one state to the other, which is anyway synchronized with the clock, my outputs are always synchronized with the clock. So these are you can also call them, these are synchronous state machines in this case, because my outputs are synchronized with the clock. In this case, on the other hand, as you can see for the Mealy type, that's not the case. If my inputs are not synchronized with the clock, if my input changes during a clock cycle, my output also can change. Right? My outputs need not be synchronized with the clock if my inputs are not. In this case, so it's not compulsory that my outputs for a Mealy type are synchronized with the clock. So we can call this the asynchronous state machines. Mealy types are more of a asynchronous state machines, because my outputs are not synchronized with the clock. In this case, they're automatically synchronized with the clock. Okay, so oftentimes because your outputs are functions of the state itself, oftentimes Moore type state machines, as you will see, would consist of a few more number of states than you would do for a Mealy type. So there are pros and cons for each type of state machine when you're actually designing them, and we'll look at some of these examples when we actually design state machines for actual systems. You will see the difference. We'll try to design them both as Mealy type and Moore type. Okay, so that's the idea. All right, so those are the two types. I hope that makes sense. And now let's move on and let's look at some additional examples of state machines. Again, going back to the last class, we did do an example on the JK flip-flop. We implemented a JK flip-flop from starting with through the entire process, right? We identified the inputs, outputs, the states. The most important thing is the states, and the way we have identified the states is the state of the output of the flip-flop itself as a state. So we have two different states associated. Either the output of the flip-flop is 0 or 1, right? And we looked at the state diagram and how the state transitions occur with J and K inputs. and we translated that information into a state table, and then we implemented that entire combinational block, the and then basically we obtained the JK flip-flop from the D flip-flop. And you've also noticed, I hope you have paid attention, that we have implemented that now after covering these two types of state machines. We have implemented the JK flip-flop as a Moore type state machine, and which is kind of obvious, right? Because we are implementing that flip-flop itself. So obviously, we want to make sure that the outputs are synchronized with the clock, because the flip-flops outputs are synchronized with the clock. Okay, so we have implemented the JK flip-flop as a Moore type machine, where my outputs are functions of the state itself. If you go back to your notes, you will realize that. Okay, so with that, let's look at some additional examples. How about implementing a counter? Now, we have looked at an example of a counter before. We have implemented a counter as a ripple counter, a synchronous counter, right? We have also looked at the example of implementing a counter as a synchronous counter, which was not a very obvious method or approach of implementing that. Of course, you can do it if you have a lot of practice in the design of such circuits, but that's not. It was more of an intuitive approach than you have followed a set technique, right? So now we will actually follow the set technique. We'll try to implement a counter, a synchronous counter, as in the counter is basically synchronized with the clock, okay, with the master clock. All the components of the counter are synchronized with the master clock, okay. Now, and implement it as a state machine. So I will talk about, again, my goal is to provide you with different examples of, because again, it boils down to, these problems boils down to, the critical step boils down to identifying the state itself. What constitutes the state for a particular example, for a particular design problem, right? Now, for the counter, in this case, let's say we want to design a 4-bit counter, or let me put it this way, a modulo 16 counter that can count from 0, 0, 0, 0, 0, 0, 0, 1. You can count up all the way to 1, 1, 1, 1, and then reset to 0, 0, 0, 0, and count up again. Okay, something like this. Each count, of course, synchronized with the master clock. So with every clock pulse, you're counting ahead. Okay. All right. So how do we design this? How many? Let's say again we want to design this as a state machine. Right. We want to design this as a state machine, and any suggestions on what constitutes my state here? What should I look upon as a state in the design of a counter? Any ideas? Or how many states should I have in this design? Okay, let's see what you have. Okay, so in this example, my each count can itself be counted as a state, right? Each count, the count value. Is counted as a state, right? So in this case, if I want to, and of course, how would you design this? Would you design this as a Mealy type state machine or a Moore type? I'm trying to design this as a state machine. I'm considering the count itself as my state, and of course the count itself is the output of that counter. So in this case, my obvious choice would be to choose the Moore type. So counter would be a Moore type state machine. Okay. So each of these counts if I want to design a modulo 16 counter, then I would design this. My state diagram corresponding to this counter would be so let's say S0. The output corresponding to that would be 0, 0, 0, 0, and which is nothing but the encoded digital binary value for S0. And then S1, S2, S3, S4, and so on. So you have 15 S until 15, right? S15, 1, 1, 1, 1. S1 will be 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, and so on. And finally 1, 1, 1, 1. And what would be the state transition? Basically, with each clock pulse, I'm going from one state to the next count, one count to the next count. There are no explicit inputs here, and that's possible. I'm simply transitioning through these states in this sequential fashion with each new clock pulse, right? with each new active edge of the clock. Okay, so this is what I have for the counter, and of course this S15 to S0, and the counter basically cycles through these counts. Again, I've designed this as a Moore type. Why? Because the outputs are nothing but the state itself, the state values itself, or the variable values itself, right? I don't have to have separate outputs here for this particular example. Although that can be for other state machines, we may need separate outputs. Okay, but in this case, it's very simple. So I encode my each state. Again, I have 16 different states. That means I have to have at least 4 state variables, right? So I encode them in these state variables A, B, C, D. Okay, so that's the encoding for S0 state. That's the encoding for S1 state, encoding for S2 state, and so on. Now, once you have the state diagram, the rest of the process is pretty straightforward. You translate that information into the state table. Okay, again, you follow the same format, right? You follow the same format each time when you're designing a state machine. So the major part is done. I've come up with the state diagram. So now the implementation would look something like this. So again, my state table the first column would be the present state. In this case, I don't have any explicit inputs, so I skip that column. Otherwise, I would have had that column. And the next state here. In this case, I don't have to have an explicit output here. I can simply take the output, the state value itself as the output. Okay. So in this case, my present state is A, B, C, D. The next state is A plus, is expressed as A plus B plus C plus D plus. Okay. And I look at all possible combinations in the present state. So I have 0, 0, 0, 0, 0, 0, 0, 1, so on, all the way down to 1, 1, 1, 1. Okay. Now going back to my state table, let me actually put one more here, 0, 0, 1, 0, so on. Now let me actually go back to the state table and then look at the transitions. So if I'm in this particular state, 0, 0, 0, 0 in the at a given instant, the next state transition would be going to S1 state, right? Because I'm basically designing a counter. My S1 state, so in the next clock transition, I'll be going to S1 state, which is basically encoded as 0, 0, 0, 1. So 0, 0, 0, 1. Okay. If I'm in 0, 0, 0, 1 state, which corresponds to this state, in the next clock transition, I'll be transitioning to S2 state, which is 0, 0, 1, 0. So if I'm in this state, that's my S0 state, that's my S1 state. I'll be going to S2 state, which is 0, 0, 1, 0. And likewise, this is S2 state. If I'm in S0, 0, 1, 0 state, in the next clock transition, I'll be moving to S0, 0, 1, 1 state, and so on. So you can basically populate this table simply from the state diagram. And now all it boils down to is you go back to your block diagram, right? In this case, I don't have any outputs, any inputs, any explicit inputs, so I ignore that. The only things I have are my present state values. Okay. All right. So the only things I have are the present state values A, B, C, and D. The next state, A plus, B plus, C plus, D plus, and of course you need to design this combinational blocks, the relationship between A plus, B plus, C plus, D plus with A, B, C, and D, because A plus, B plus, C plus, D plus are functions of A, B. Each of these outputs are functions of A, B, C, and D in this combinational block. And of course, now we have 4 flip-flops, DA, DB, DA, DB, DC, DD, QA, QB, QC, QD. And each of my flip-flop is of course clocked, and you can assume that each of my flip-flop is internally connected to that master clock. And of course you have the feedback that's basically common to every state machine. So all it boils down to is to design this relationship between A plus and ABCD, B plus and ABCD, C plus and ABCD, and so on from this state table. So you implement A plus as a function of A, B, C, and D using the K-map approach, implement B plus, C plus, and D plus, and you will get the synchronous counter designed as a state machine, or using the state machine approach. Okay. All right. So that was the example of a Moore type design, okay, for the design of a counter. I hope that makes sense. Again, my goal is to come up with different examples of state machines that can be implemented, and the most important thing when you're trying to design them is how would you associate the state? What do you mean by the state in the design of that state machine? In this case, as in this particular example, the state itself, the count itself becomes the state of that particular state machine. All right. Any questions on this example? Does that make sense? You will have similar problems on the homework. So yeah, go ahead. You have similar problems on the homework, so make sure you do the homework. Anybody had a question there? Okay. Okay, now let's look at another example. Let's now, so far in the design of adders and subtractors, right, we have looked at them as applicable for parallel addition, parallel operations, right? Parallel operations as in you're applying all the input at once. The adder basically has all the inputs applied, and the adder performs the addition. Let's say you have you're trying to add two n-bit numbers. Okay, that means you have to have an n-bit adder there. Okay, that can be, and you basically apply those two n-bit numbers to that n-bit adder. The adder perform and then basically performs the operation, provides you with the output and the carry out. Now, an alternate way of dealing with things is through serial operations, and we deal with that every time. in your actual experience, serial operations. In this example, when you're working with serial operations, we are dealing with these bits that are synchronized with the clock, and we are dealing with these bits one bit at a time. Instead of looking at all of them at once, these are basically looked at one bit at a time. Okay, so your bits are coming one bit at a time, synchronized with the clock. Okay, and then let's say you want to add, you want to design a serial adder. Now the advantage of this, a serial adder, is that you can have a single bit adder. I can basically have a single bit adder, and I can use that to add n bits together in a serial fashion. Of course, I cannot do it parallelly, but I can do it in a serial fashion. The idea here is, let's say I have this adder. I'm trying to design this, of course, all right? And let's say I have two, this is a single bit adder. That means I have two inputs, x and y, right? And sum and carry out. And of course, I have C in as well, all right? So that's a single bit adder, okay? What I'm trying to do here is, let's say these are my bits coming in, one bit at a time. Are you able to see this properly? All right. Okay. So these are the bits coming in, one bit at a time. I'm applying these. These are all synchronized with the clock. Okay. So that's my X input, and so on. These are coming in serially, one bit at a time. So let's say that's my n bit numbers, and I'm trying to add them together. Okay. Providing a sum, and let's say in this case I'm trying to add these two bits together, and I am trying to store that sum. And this is where we can actually find some uses for the shift registers, right? Let's say this is an n-bit shift register. I'm trying to add these two together, these bits, along with the previous carry, okay, and pushing the sum, the resultant sum, into this shift register. Let's say that's my input of the shift register, so that's an n-bit shift register. I'm pushing that sum into that. Of course, this is clocked. Okay, so with each clock pulse, I'm sending in one bit at a time, my serial inputs, one bit at a time. This adder adds these two bits along with the previous carry. Okay, so again, if you recall, the way we add them, let's say you're adding these two numbers together. Okay, right? I add these two bits together. Now, when I'm trying to add these two bits together, I have to consider the previous carry, right? The carry that was obtained when I added these two bits together, the previous bits together. So I have to consider that carry as well, right? And then I add them together. I get some sum, and then I repeat the process. So every time I'm adding these two bits, I need to have some kind of a feedback. I'm generating a carry out when I'm adding these two bits, and those and for the subsequent bits, I need to consider adding this carry out along with the two bits together. Okay, I hope that makes sense. So in this case, and everything has to be synchronized with the clock. So in this case, the obvious choice is to have a flip-flop here that takes in the carry out information. Let's say that's TA, QA. That's synchronized with the clock, the same master clock. Okay, so that's clocked. So this clock signal is of course the same as this, and this C out, you have that feedback, so that every time I add two new bits, I'm also considering the previous carry in, the previous carry generated. I'm adding the previous carry along with the two bits, producing a sum that is being shifted through this n-bit shifter, n-bit shift register. So after n clock cycles, I would have had the entire n-bit sum. Right. I would have shifted the entire sum, into my shift register. And of course, I can basically, these two could also be two shift registers that stores that those n-bit numbers, and with each clock pulse, I'm sending in one bit to these, one bit from each to this adder, one bit adder, and then by this arrangement, I've essentially derived a serial adder. So in this case, I'm not limited by the size of the bits. Of course, I still need to have that amount of the size of these registers, but for the adder itself, I can add any large number together, right? Because now it's a single bit adder, but because of the serial operations, I'll be able to, I'm not limited by the size of the adder to add two large numbers together. Okay. So, of course, in this example, as you can see, I'm going backwards. I've come up with the design of the state machine. This is a state machine. Now let's actually look at how the state diagram would look like for an n bit for a serial adder. Okay. So this we have already realized this. This is exactly what we will derive, even if we go through the initial approach of the state diagram and then state table and deriving the combinational block. You would have probably derived the same thing. But now let's go back and getting the clue from this. Let's now decide the state, what constitutes a state for an adder, and what kind of a state machine would that be? Okay, let's let's do that. Okay. So let's say I'm trying to design a state machine, or I'm trying to design a serial adder, a single bit serial adder using the state machine approach. Again, I will go through the steps, through the protocol, if you will. First thing is my inputs and outputs are identified. My inputs are X and Y. These are serial inputs, 1-bit serial inputs. As in, you get 1 bit from each, synchronized with the clock. Then I have my outputs are sum and carry out for this particular adder. Okay. Now the state. What constitutes the state? How do I define? Again, you have the clue right there, right? What constitutes a state when I'm trying to design a serial adder there? Okay. And how many states should I have? All right. So in this case, I can define my state, okay, as 0 as a state where my carry out is 0, where I don't have to add a carry out. My carry out, C out is 0. S1 as a state that does have to add a carry out, or my carry out is 1 in this case. Okay. A state where my carry out is 0, a state where my carry out is 1. Okay. And now let's actually design this state table, state diagram for this particular state machine. So we have this. Let me take this out. We don't need this. Again, remember that the way we have designed this, you should have this in your notes. So I have S0 state based on the carry out produced. S1 state. Here my carry out is 0. Here my carry out is 1. Okay. Now I'm adding two inputs, X and Y, right? So I'll look at all possible combinations between the inputs. So when I'm in S0 state, okay, the carry to be added to the two inputs is 0. In this case, my X and Y, if X and Y are both zeros, my carry out produced is 0. I remain in the same state. Okay, producing a sum S0 of 0. Right? That's the output. let's again, this is although this looks like a Moore type, let me not do that. So let me call that C0. That's the state defined as C0 equal to 0. This is a state defined as C0 equal to 1. Okay. My outputs are still S0 and S1, S0, right? So xy equal to 0, 0. The sum is 0 plus 0 plus 0. The sum is 0. I do not produce a carry out, so I remain in the same state. Right? The carry out is still 0. I look at all possible combinations between x and y. If x equal to 0, and y equal to 1, I remain in the same state. X equal to, or xy equal to 0, 1. My sum in this case is 1. The carry out is still 0. I do not produce a carry out, so I still remain in the same state. Now xy equal to 1, 0, same thing. I'm adding 1 plus 0 plus 0, that's still 1. Sum is 1. There is no carry out produced, so I'm still in the same state. Now xy equal to 1, 1. So the sum is 1 plus 1 plus 0. Okay, 1 plus 1 is 1, 0. So I have a carry out. That means I need to transition to the next state because that's the state where my carry out is a 1. So for xy equal to 1, 1, when I'm in a C0 state with xy input of 1, 1, my sum as 0 is 0, the carry out is 1, so I transition to the next state. So I'm done with C0. I've looked at all possible combinations between the inputs. Now I move on to the next state. Okay. All right, I'm in C0. So I'm in, okay, let me see. Okay, fine. C0 equal to 1 state. Okay, just make sure, I just want to make sure that you distinguish between these two states. The way I've defined these two states is, again, C0 is 0 here, C0 is 1. Now, when I'm in C0 equal to 1 state, with xy equal to 0, 0, xy equal to 0, 0, what is my sum? I'm adding 0, 0 to 1, so then my sum is 1, my carry out is 0, right? So I move to the next state. With xy equal to 0, 0, the sum produced is 1, but I do not produce a carry out. So that's why I transition to the state where I did not produce a carry out, which is C0 equal to 0 state. With xy equal to 1, 0, or xy equal to 0, 1. So I'm adding 0 plus 1 plus 1 here because I'm in this state, right? That gives me a sum of 0, sum of 1, 0, or the carry out is 1. So I remain in the same state. Xy equal to 0, 1. So 0 plus 1 plus 1 produces a carry out of 1. So I remain in the same state. My sum is 0 is a 1, is 0. Because the sum is 0, the carry out is 1. With xy, same thing for xy equal to 1, 0. I remain in the same state. Xy equal to 1, 0. My sum is 0. Okay, let me write this here. I remain in the same state with xy to 1, 0. Sum is 0 equal to still 0. And finally, with xy equal to 1, 1. So I'm adding 1 plus 1 plus 1 here because I'm in this state. That produces sum of 1, a carry out of 1. So I remain in the same state with xy equal to 1, 1, producing a sum as 0 as 1 and a carry out, so I remain in the same state. Okay, and that's it. So that's the design, or that's the state diagram for a serial adder. Okay. And it is in this case we are implementing this as a Mealy type machine. This is obvious from the way we have expressed the inputs and the outputs. So the outputs are expressed along with the inputs. So my outputs are functions of both the state and the inputs. So that constitutes a Mealy type machine. Okay. Again, the major challenge when you're trying to design state machines is how do you constitute the state? How do you define the states for that particular state machine? And once you've come up with a good idea about how to do that, then the rest of them becomes a little bit more easier, okay? More straightforward. But that's why I'm trying to come up with multiple different examples, so you have a better idea, diverse ideas about how we can go about that. Any questions on this, on the implementation or the state diagram for a serial adder circuit? Okay, let me do this. Yeah. So let me define this here so that there's no confusion. A zero state as a state where C0 is a 0. There's no carryout produced. As one state as a state where my C0 is a 1. The carryout produced is a 1. That's how I define this. So I have only two states. That means I need to have a single state variable, a single state variable constitutes a single flip-flop. And when you put this information down on the state as a state table and implement that, you will exactly get the circuit that we have just discussed before we drew the state diagram, where we had a single adder and then you had the feedback. So you'll be basically the combinational block constitutes that single bit adder in that case. You will basically derive that single bit adder circuit as the combinational block, and then you have of course you have the feedback that goes down for any state diagram, state machine. Any questions there? Okay, let me check.
I don't really have a question, but so like you're saying this is more like a guide how to set up the circuit later?
Yes. So in this case, once you have the state diagram, setting up the circuit should be, if you just follow through the technique, you should be able to set up the circuit. Okay.
Okay.
But the important thing is the state diagram. And of course, in this particular example, just to show you what constitutes a state for a serial adder, I came up with the circuit first to make it a little bit more obvious. So that was the idea behind actually coming up with a circuit first and then getting a clue from that and then translating that information into a state diagram. I kind of went backwards here. Typically, we go from the state diagram to the circuit. We came from the other way around here. Okay. Now you have other examples in the homework, so I hope you'll have fun doing them. Actually, they are fun examples. All right. Now, let's see how we're doing on time. Then, okay, well, we're okay. Now, let's look at some other examples of, okay, now the screen is frozen. That's not good. Don't like that. The free screen gets frozen. All right. Okay. Now let's start working on a class of circuits. Now let's actually design a class of circuits called sequence detectors. Okay. So why do we need them in the first place? Again, sequence detectors are needed when we're doing the serial operations. Okay. Typically, as we kind of discussed before, when we discussed the when we discussed the parity generators, right? The way we transmit information is through packets. Okay. So you have a communication channel, all right, and your information is transmitted serially, okay, in packets. Basically, each packet consisting of a fixed number of bits. So let's say you have 4-bit packets or 8-bit packets. Let's say 8-bit packets, which consist of the data. This is all the data that you're trying to transmit through the communication channel, and then you're at the receiving end. you are receiving this information 1 bit at a time, again synchronized with the clock. Okay. Now, when we're trying to transmit these information, all right, how do I distinguish between different packets, right? And one way of doing that is to have a known sequence, okay, that we have appended to each packet. Okay, so that signifies, okay, this is the start of the sequence. So once I identify that sequence, I will know exactly, okay, this is the start of the sequence, that's the end of the sequence, or that's the start of the sequence, that's the end, there's the start of a new sequence, and that's the end of the sequence, and so on. So I need to have an ability to identify these patterns, okay, or the patterns of bits in this case, okay, so that I can basically transmit them. I can tag along these known sequence bits to my data packet, send it, and at the receiving end, I will know where my start of the sequence is, where my end of the sequence is, and what the data is between, which is sandwiched between those two unique sequences. Okay, so that's the idea. So I need to have a circuit that can identify a known sequence. Okay, so let's say I would like to design a circuit. Okay, in this case, which would identify a sequence 0, 1, 0 as a start. What I mean by that is, if I have a stream of these bits, 1, 0, let's say if my x is 1, so these are the input stream of bits that are coming through my communication channel. Okay, now I would need to come up with a circuit that can provide me an output every time that sequence is detected. Now, in this case, where are the instances where the sequences are being detected? So as you can see here, this is one instance, right? I've identified this sequence here. That's one instance. This is another instance. Okay. Where else we have? This is another instance where I've identified a sequence. Here is another instance where I've identified a sequence. And of course, let's assume that this is 0. Oh, it's the same. Because I may have overlapping sequences also, right? So in this case, let's say this is, and depending on how you specify, sometimes I would like to identify overlapping sequences as well. Sometimes I don't want to identify overlapping sequences. So let's say in this example, I would like to identify overlapping sequences also. So here I have a sequence 0, 1, 0 identified. Now here I have another sequence because this 0, 1, 0 is also here. That's an overlapping sequence. For this particular example, let's say that that's also counted. Okay, that's another sequence that I identified in my input stream. So my output should be, every time I identify the sequence, at the end of the sequence, I should output a 1 to signify that I have identified, my circuit has identified that particular sequence. All right. So my output will be, every time I identify a sequence, I've identified a sequence here. At this instance, so I output a 1. Again, 0, 0, 0. I've identified a sequence at this instance, I output a 1. Then zeros, all zeros. I've identified a sequence here, I will output a 1. 0, again, that's an overlapping sequence, but since that is allowed, I will output a 1 here as well. 0, 0. Another sequence identified here, that I'll output a 1 here, and so on. So we need to design a circuit that can do this operation, a sequence detection in the input stream. So that's my input stream, that's my output. Every time I identify a sequence, in this case, again, overlapping sequences are allowed. So every time whether it's overlapped or not, I would need to output a 1 for the identified sequence, overlapping sequences. So that needs to be specified in your problem statement. Sequences are allowed. Then that is typically specified if they are allowed or not allowed. And of course, your state diagram can change depending on if it's allowed or not allowed. And we'll take examples of both types. Okay. All right. Now, so we have the problem statement. We know what the inputs are. We have the input X, and we know what the output is. We know what the output is. The output is Y. Now we have to identify the states. What constitutes a state here? How do we define our states for this particular state machine? Once I have identified that, then the next step is to come up with a state diagram for this particular circuit, okay, and implement it pretty much, okay. All right, so let's do that. So how do I define my states? So in this particular example, since the sequence is x equal, since the sequence I have to identify is 0, 1, 0, okay. So I have to have a capability to remember that, again, these inputs are coming in one bit at a time, right? I should have a capability to remember that that a part of a sequence has occurred already. For example, if a 0 has occurred, I need to have a state that would identify that a 0 has occurred, or that would remember that a 0 has occurred in the sequence. And if you remember that a 0 has occurred, then I have to have another state that would remember that a 0, 1 has occurred, another state that can remember that the entire sequence has occurred. So I have to keep that in mind. I have to have a state machine wherein I have a state. Let me call that the reset state, and you'll see why we need that. Let me call that the reset state, because every time I don't identify a sequence, I need to reset and start counting again. That's the idea behind the reset state. I will associate a state S1 as a state that has identified that a 0 has occurred, the first 0 has occurred, or identified or recorded. Let me put it that way. Recorded that a first 0 has occurred. 0 occurred. That's how I constitute my state here. Okay. I would define my S2 state as a state that has identified or recorded that a 0, 1 has occurred in the sequence, because 0, 1 is part of the sequence that I need to identify. Okay. And let's see if I can build my state diagram. Okay, let me actually build, let's say, 3 state as a state that has identified or recorded that a 0, 1, 0 has occurred. Okay. So that's how I define my states in this case, right? And now with that information, let us draw the state diagram. How many states do I have? I have 4 states. Okay. So how many state variables should I have? I have 4 states. The next step, or the next decision that I have to take is, should I implement this as a Mealy type state machine or a Moore type state machine? In this example, let's actually do both ways. Okay. At least for now, at least let's do one type. Let's start with the Mealy type. Okay. I have identified that we have 4 states, and let's try to implement this as a Moore type state machine. Now, if I have 4 states, how many state variables should I have? Again, I need to encode each state with a unique binary code, right? And the minimum number of bits I should use to encode my states, individual states, that decides how many state variables should I have in my state machine construction, right? So in this case, I need to have at least 2 bits to encode each state. Okay. So I would use 2 state variables, 2 bits to encode each state. Implies 2 state variables, and that corresponds to using two flip-flops in your design, right? Because each state variable will have its own flip-flop associated with it. Okay, so that's good. 4 states. I'm implementing this as a Moore type state machine. I have 4 states, so each state needs to be encoded with a unique binary code That means I need to have at least 2 bits to encode each state with a unique binary code. That means I need to have 2 state variables in my design. Okay. Now let's actually draw the state diagram now. So I start with a 0 state. A 0 state is supposed to be the reset state, and I'm implementing this as a Moore type, so that my outputs are specified along with the state, the Moore type, right? I'm in a 0 state. If an input of x equal to 0 occurs, that means my first 0 has occurred. That means I need to go or transition to a state that has identified that a 0 has occurred. That means I need to transition to the S1 state. Of course, when I'm in a 0 state, my output y is 0 because I've not identified any state, identify the sequence, so my output is 0. Now I'm with x equal to 0 input, because I've identified S1 as a state that has recorded that a 0 has occurred. That means I have to transition to S1 state. I have not identified a sequence yet, so my output is still 0. Okay. X equal to, let's say if I'm in the reset state, and if x equal to 1 occurs, now 1 is not part of my sequence, 1 is not the first bit of my sequence, so I need to reset and start looking forward for the next bit, right? So if I'm in the reset state, which is S0 state, if x equal to 1 occurs, I remain in the same state. I reset and then start looking for the next bit. Okay. If the next bit is x equal to 0, then of course I transition to S1 state. Okay, so I'm done with the S0 state. I'll go to S1 state and do the same analysis again. I'm in the S1 state. That means a 0 has been recorded already. Okay. Now let's say if I'm in S1 state, a 0 occurs. Okay. I'm in S1 state. That means a 0 has already been recorded. It's something like this. My input sequence has 0, took me to S1 state, and another 0 occurs. Okay. Now 0 is the starting bit of a sequence, right? So now instead of considering this as my starting bit, I would consider this as my starting bit, right? And start counting and start recording again. So in this case, if I'm in the S1 state, which has recorded that a 0 has occurred, with x equal to 0, I remain in the same state and start counting this new 0 as a recorded 0, as my first 0. So that takes me back to the same state. All right. And the other possibility is x equal to 1, right? If x equal to 1 occurs, what happens? That means I have 0. I have in my input stream. This 0 has been recorded by S1. Now a 1 occurs. That means now 0, 1 is part of the sequence. And I have defined S2 state as a state that has identified that a 0, 1 has occurred in the input stream. That means I need to transition to S2 state now. Again, I have not identified the entire sequence, so that's still 0. My output is still 0. So with x equal to 1, I transition to S2 state. Okay. All right, so I'm done with the S1 state. I looked at all possible combinations of the inputs. Now I move on to S2 state. S2 state is a state that has identified as 0, 1 has occurred. Okay. Now if I'm in S2 state and let's say x equal to 0 occurs. So 0, 1 in the input stream takes me to S2 state and a 0 occurs. Now I have identified the entire sequence. I defined S3 as a state that has identified the entire sequence 0, 1, 0, S3. So I transition to S3 state. Now since I've identified the entire sequence, my output should be a 1. So x equal to 0 here takes me from S2 state to S3 state. Okay. What happens if 0, 1, let's say, if I'm in S2 state, which has identified as 0, 1 has occurred, and a 1 occurs in the input stream, 0, 1, 1. Now, I cannot have an overlapping sequence. This is not part of the sequence. So now I just reset. I have to reset and start looking for the next 0, right? It's not part of the sequence. So if I'm in S2 state, and a 1 occurs in my input stream, then I will need to basically transition to a 0 state, which is the reset state, and start counting again in the input stream. So now I'm done with the S2 state. I move on to S3 state, which is the state that has identified that a 0, 1, 0 has occurred. All right. Now I'm the S3 state. That means a 0, 1, 0 has already occurred. And let's say 1 occurs now in the input stream. S3, this 0, 1, 0 in the input stream took me to S3 state. Now a 1 occurs, let's say a 0 occurs. Let's start with 0. A 0 occurs now in the S3 state. Now this 0 could be the start of another sequence, right? That means I need to transition to a state which has identified or recorded that a 0 has occurred. So when I'm S3 state, if 0 occurs, then basically I need to transition to S1 state. X equal to 0 takes me to S1 state. All right, so I'm done with that possibility. What happens if I have a 1 occurring in the input stream? I'm in S3 state. That means that took me 0, 1, 0 in my input stream, took me to S3 state. Now a 1 occurs in the input stream. All right. Now what happens? Now this 0, 1, because overlapping sequences are allowed, this 0, 1 could be part of another sequence, right? So I need to go to the state that has identified that a 0, 1 has occurred in my input stream, which is basically S2 state. So if I'm in S3 state and x equal to 1 occurs, that transitions me back to S2 state. And that is it. So I've looked at all possible combinations for the inputs for each state, and I drew the state diagram. And that's the state diagram, a Moore type state diagram, or Moore implementation of this sequence detector. Okay. So I think we are out of time. So what we will do is we'll stop here, and in the next class we'll actually implement that. We'll also implement the Mealy version of this state diagram or this sequence detector, and implement that and look at the difference between those two in the implementation. All right. Any questions here? I know we are kind of out of time. I will be uploading the lectures today. Absolutely right. So yes, I'll be uploading the lectures. So you'll have some reference to look into. Yeah. All right. So with that, let's end this class. And yes, there will be a practice exam like I posted last time. So you can have some idea about what kind of questions will be expected on the exam. Okay. So yes. Let me stop recording here as well. Okay, so if you don't have any other questions, then I'll see you guys on Thursday. So we'll have some review as well on that day. Wrap this up, and we'll have a review as well. Okay, great. Thank you. You too. Have a good day.